Welcome back to our course on mechanical behavior of materials part 2. So in the last class, we were talking about determination of plastic zone size ahead of the crack tip. Okay. So we discussed first about how to determine the value of Ry, and then we incorporated Irwin's correction, and then we calculated the value of Rp, and it turns out that Rp is equal to twice of Ry. Okay. And if you remember, the calculation was done only on the crack plane. That means theta was equal to 0. So in today's class, what we are going to do, we are going to talk about the plastic zone size and therefore the shape at all value of theta and r in front of the crack tip. Okay, so let's proceed. So in the last class, we had calculated both Ry and Rp. Okay, and overall we had got these two values. Plane stress, and then we have plane strain. Okay, and for plane stress, we had obtained 1 by 2 pi K1 by sigma y square. For this, it was 1 by 6 pi K1 by sigma y square. And Rp is just twice of Ry. Okay, so it is going to be 1 by pi K1 by sigma y square. This one 3 pi K1 by sigma y square. So overall, in the plane strain condition, the plastic zone size is smaller than plane stress condition. And we had calculated this on this crack plane, right? That means theta was equal to 0. Okay. So what we are going to do now is to calculate the plastic zone size at all angle of theta. So we are going to determine what is happening here. Okay. So at theta and at a distance of r, okay, ahead of the crack tip. That is what we are going to do now. Okay, so we are going to calculate shape of plastic zone. Okay. Now, if you remember the derivations we had for Irwin's, we had calculated the value of sigma 11, sigma 22, and tau 1. Okay. So sigma 11 was A1 divided by root 2 pi r, then cos theta by 2, 1 minus sine theta by 2, and sine 3 theta by 2. Similarly, sigma 22 was A1 divided by root 2 pi r cos theta by 2, 1 plus sine theta by 2, sine 3 theta by 2. And the last is A1 root pi r, then cos theta by 2, sine theta by 2, and cos 3 theta by 2. Okay, so if we have a track here, and if I take a small element here, so it's a point which is like an element, and if I blow it, so this one we had already discussed, right? So something like this. So at that particular point, we are going to have sigma 11, sigma 22, And then in these directions, you have tau 1. Okay. So this we had discussed. So now let's use this to calculate what is going to be the plastic zone size ahead of the crack tip. Okay. Now remember when we were talking about the crack plane, tau 12 is 0. So the sigma 11 and sigma 22 automatically become principal stresses. Okay. So it was very easy to use directly the value of sigma 11 and sigma 22 in Tresca criteria and von Mises criteria. Okay. But now since we are talking about at all angle and the R value, right, it is not going to be principal stresses. Okay. So first of all, what we have to do, we have to calculate what is the principal stress value at different points. Okay. And then we use those principal stresses values in Tresca criteria and von Mises criteria to calculate what is going to be the plastic zone size or RY. Okay, so let's do that. So first we have to calculate what is going to be sigma 1, sigma 2. Okay, yeah, that means principal stresses in terms of R and theta. Okay, so sigma 1 and sigma 2 can be given as sigma 11 plus sigma 22 divided by 2 plus minus sigma 11 minus sigma 22 by 2 square plus tau 12 square. Okay, and this was already done in course 1, part 1. Okay, so the principal stresses is sigma 1 and sigma 2. So these are your principal stresses. Okay, and sigma 1 and sigma 2 are the stresses at that particular point. So if we know sigma 11 and sigma 22 by given by Irving's, we can calculate what is the value of sigma 1 and sigma 2. Okay, so let's do that. So sigma 1 is going to be, so sigma 1 is going to be the higher value by convention. So we are going to use plus for that. So this is going to be plus. Okay. And sigma 11, sigma 22 values, we already know. You see here. So we know what is sigma 11 and sigma 22 and also tau 12. So we have to just place these values in that equation, sigma 1 and sigma 2. And now I'm going to use cos theta by 2 as c theta by 2 and sin theta by 2 as s theta by 2, because then the calculation becomes easy. The writing becomes easy. Okay. So sigma 1 equal to, you can write this as k1 divided by root 2 pi r c theta by 2 plus this whole term will be k1 root 2 pi r square s square theta by 2 s square 3 theta by 2 c square 3 theta by 2 plus k1 root 2 pi r square and then c square theta by 2 s square theta by 2 and c square 3 theta by 2. So you have to just place the value of sigma 11, sigma 22 and tau 12 given by Irving. Now if you solve this, it's going to be k1 c theta by 2. This term, and just take out k1 by root 2 pi r square. So it is 2 pi r and then s theta by 2 and c theta by 2 we can take out. So s theta by 2 and C theta by 2. Remember we have a root. So S square theta by 2 will become S theta by 2 and then similarly it will be C theta by 2 and then we are left with S square 3 theta by 2 plus C square 3 theta by 2 to the power half. Now this value is equal to 1. Sin square theta plus cos square theta is equal to 1. Okay? So now sigma 1 if we calculate is going to be K1 divided by root 2 pi r. Okay, and then let's take out C theta by 2 outside. So we are left with S theta by 2. Okay, so we know one of the principal stresses is in terms of theta. Now in the track plane, if you remember, sigma 1 and sigma 1 both are equal, and if you do that, put theta equal to 0, you are going to get sigma 1 equal to sigma 1. Okay, now let's see what is sigma 2 principal stress. Okay. So sigma 2, if you just do the same calculation what we did for sigma 1, it will be A1 divided by root 2 pi r C theta by 2 1 minus S theta by 2. Okay. So you got sigma 1 and sigma 2. Now, if you want to apply principal Testa criteria and one Mises criteria, we have to know what is sigma 3, right? And sigma 3 values are going to vary depending upon the condition, whether it is plane stress or plane strain. We have discussed that, right? So if it is plane stress, sigma 3 is going to be 0. And if it is plane strain, sigma 3 is going to be Poisson's ratio times sigma 1 and sigma 2. You know what is sigma 1 and sigma 2? So we have derived here sigma 1 and then sigma 2. So if you just place those two values, you can calculate what is the value of sigma 3, which is the third principal stress. So that will come out to be 2 mu K1 divided by root 2 pi r C theta by 2. Okay. So you know now what is sigma 1, sigma 2 and sigma 3 with respect to theta and r. So at all points in front of the tractive, you know what are the principal stresses. Now let's use these values, principal stresses values, and then use Testa and von Mises criteria. Okay. So let's first talk about the plane stress condition because the calculation becomes simple. And then we will see what happens in plane strain condition. Okay. So let me write down first the two criteria. So we are going to use Testa as well as von Mises. And then we'll compare, okay, the plastic zone size when you use these two. So Testa is sigma max minus sigma mean equal to sigma y, okay, where these two are principal stresses. And then von Mises is going to be sigma y equal to 1 by root 2, then sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square and then sigma 2 minus sigma 3 square root. Okay. And all these sigma 1, sigma 2 and sigma 3, these are also principal stresses. Okay. So now we know what is sigma 1, sigma 2 and sigma 3. We have to just place this value and then we are going to figure out the correlation between K1, Ry, theta and sigma y. what we have already done on the track plane before. Okay. So let's calculate for plane stress condition first. So here sigma 3 is equal to 0. That we know. Okay. And if we use now Tresca, then it will be sigma 1 minus sigma 3 equal to 0. Sorry, sigma y. And then sigma 3 here is 0. So sigma 1 equal to sigma y. Okay, we did the same thing on the track plane before in the last lecture. Okay. Now sigma 1 we can write k1 divided by root 2 pi r c theta by 2, then 1 plus s theta by 2. This is going to be sigma 1. Okay, so we got one relation between theta r and sigma y and k1. Now, if you put say theta equal to 0, which is on the track plane, you are going to get the same ry value what we have learned in the last class. Okay, but now we are varying the theta and seeing the changes in the value of ry. Okay, in front of the track plane. So overall, we can write here that. So let's move root r on the right side. So we can write k1 divided by root 2 pi c theta by 2, 1 plus s theta by 2. And then we have sigma y here. So root r. Now let's take square. So ry in terms of theta, we can write 1 by 2 pi k1 divided by sigma y square. And then you have this big term square. So we have got a term, a relationship between ry and theta. K1 is known, sigma y is known, and if we know theta, we know what is ry. So if we have a track here, what we have to know is this theta value. So at different theta, you can calculate what is the value of ry because we know the value of k1 and sigma y. Now if you put theta equal to 0, the value of ry is 1 by 2 pi k1 by sigma y square, which we have already calculated before. So it is valid for theta equal to 0 also. Okay. So this is for Tresca. Now let's do for von Mises. So if we use von Mises, it is sigma y equal to 1 by root 2 sigma 1 minus sigma 2 square plus sigma 1 minus sigma 3 square plus sigma 2 minus sigma 3 square. We know sigma 1, sigma 2 and sigma 3. So we have to just place those values here. Okay. So we can write this as sigma y 1 by root 2. And in all the cases, sigma 1, sigma 2 and sigma 3, we have a common factor of k1 by root 2 pi r. So let's take that out. Place sigma 1 and sigma 2 values. You are going to get c theta by 2 plus c theta by 2 s theta by 2 minus c theta by 2 plus c theta by 2 s theta by 2 square, that is sigma 1 minus sigma 2 square, plus sigma 1 square is c theta by 2 plus c theta by 2 s theta by 2 square, and similarly we are placing the value of sigma 2. Okay, we solve further. Going to be 1 by root 2 a1 by root 2 pi r. Okay, then these two will cancel out. So we can write 4 c theta by 2 square s theta by 2 square, and then let's combine the second and third terms here. That will come out to be 2 c theta by 2 square, and then 2 c theta by 2 square and s theta by 2 square to the power half. Okay. And then we can write this as sigma y 1 by root 2 a1 divided by root 2 pi r and 2 c square theta by 2 plus 6 c square theta by 2 s square theta by 2 to the power half. And then this 6 we can write as, say, 3 into 4 divided by 2. Okay. And why we are doing this? Because now we can combine 4 s square theta by 2 sine square theta by 2, and this will be sine theta square or sine square theta. Okay. Because sine theta is 2 cos theta by 2 sine theta by 2. Okay. And then we can also write 2c cos square theta by 2 as 1 plus cos theta. Okay. So overall, if you solve, it is going to be sigma y 1 by root 2 a1 divided by root 2 pi r, and this we can write as 1 plus cos theta plus 3 by 2 sine square theta to the power half. And then just move the r there and take square. You can write ry in terms of theta is going to be 1 by 4 pi a1 divided by sigma y square, then 1 plus cos theta and 3 by 2 sine square theta. Okay. So we have got the value of ry in terms of theta in the plane stress condition for both von Mises and Tresca. So if we can just place the value of theta, we should be able to plot the plastic zone size, and then we know what is the shape of plastic zone. Okay, so that was for plane stress. Similarly, you can do for plane strain. So here sigma 3 is not 0. Sigma 3 is going to be 2 mu a1 divided by root 2 pi r, then c theta by 2. Okay. So you have to just place now again the value of sigma 1, sigma 2 and sigma 3 and utilize Tresca criteria and von Mises criteria. Okay. So for Tresca, you have to place value of sigma 1 and sigma 3 equal to sigma y. So this is your Tresca criteria. Again here sigma 3 is not 0. You have to utilize sigma 3 as this. Okay. So this is your Tresca. And for von Mises, it is going to be sigma y equal to 1 by root 2 sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 1 minus sigma 3 square to the power half. Okay. So this becomes your von Mises criteria. Okay. So instead of sigma 3 equal to 0, we have to place sigma 3 as this, and you should be able to now obtain the relationship between ry in terms of theta. Okay, for both Tresca and von Mises in plane strain. So you can actually use MATLAB to plot it. Okay, so if we plot both von Mises and Tresca and in both plane stress and plane strain condition, let's see how the plot looks like, and you can do it using MATLAB or any other software. Okay, because we know the relationship between ry and theta. So if you use von Mises, going to be your plastic zone shape is going to be something like this. Okay, it's like dumbbell. Okay, and then that is in plane strain, and in plane stress it is going to be larger. We know that. Okay, so this is the schematic. You can actually get a nice plot using MATLAB. Okay? So this one, the larger one is for plane stress, and the smaller one is for plane strain. So this is for von Mises. We can do the same for Tresca. So if we have the same crack length, okay. So for plane stress, you are going to have larger for Tresca than von Mises. It is going to be something like this. Okay. And if we just do plane stress, it's going to be something like this. So this is for plane stress, okay, and the blue one is for plane strain. Okay, so now you know the plastic zone size as well as shape for both von Mises and Tresca, as well as in plane stress and plane strain condition. Okay, so this is the general condition. What we did in the last class was for track plane. So we calculated actually this particular value. So what we did in the last class was we calculated for the track plane. Okay, which is this particular value here. We calculated this value. Okay. So overall, if you see, plastic zone size for plane stress is greater than plane strain condition, that we already know. And here if you see, it is more for Tresca than von Mises. Okay, so we have calculated the plastic zone size and shape for both von Mises and Tresca in this lecture. Okay, so I will stop here, and in the next class we are going to discuss more about the fracture mechanics concept based on the configuration. So what happens when you have different kind of sample dimensions and configuration? What is the value of stress intensity factor, etc. So we are going to discuss about that in the next lecture. Okay, thank you.